welcome back to another lecture. In fact, this is the last lecture now in this operating system series, but it's quite an interesting one. It's quite nice because it demonstrates how far we've got through these lectures. What we're going to do today is bootstrap our own C kernel. So we're going to write a kernel in C, just a very small C program, and but we're going to boot it all from our assembly boot sector. So we're doing it all without any support from any other libraries or anything like that. So it's real low-level stuff, but we've come a long way if we can start executing C code. Once you get into C, out of assembly, you can start to be more productive, and you can start to really start to layer up abstractions to build your operating system. I'll leave that for another lecture series. Maybe I'll do something later on, or somebody else will pick it up. Yeah, I hope you've enjoyed these lectures. I hope that it sort of inspires you to go and look for yourself to find out more about this stuff. Sometimes it's very difficult to get started, and if you just have a little sort of if you just have something you can start with, then it helps you to go off and find these things. Now we've got the internet these days, it's great for finding out information. It used to be much harder. You'd have to get very specialist books, and even those wouldn't cover everything, but we're quite lucky to have the internet. Okay, so let's get on then. So what we're going to look at, bootstrapping a C kernel. So far we've been playing in assembly, and we know now how difficult assembly is. I'm always making mistakes. I forget the syntax. I'm probably writing on day to day, I'm writing about 3 or 4 different languages, and I get them all mixed up. So it's easy to do that, especially in assembly. So we're going to get into C. But before we just go off and try and load a kernel, I want to, like I've done with some of this stuff, I want to explore how the compiler works. What does the compiler generate when we run a C compiler? If we, like we've been doing before, we've been looking at the binary, like in a hex editor and stuff, of our boot sector code we wrote in assembly, and I'm going to do now the same in our C generated code. And I'm just going to build up with some examples of how the compiler generates code in assembly, and it should demystify it a bit. You'll see that the C code is just translated into assembly code, and if we're going to be loading our C kernel, we need to understand how that binary code is laid out in the files. How is it formatted inside the files that the compiler generates. So let's start off then with some examples. Okay, so what we're going to do, well, I'm just going to dive straight in really. I've got some commands here that I've just prepared, and I'm going to explain what they are and why we use them like we do. And it might be a bit overwhelming when you look at all of the commands I've got in here for doing this stuff today, but it's really just a case of you just chain things together, and that's how you create your build chain. I'm purposely not using things like make. So make is a very nice way to script and build, to do like build scripts to build code. But I'm not using it because I want to show all of the individual steps. You can go away with these examples, and you should be able to create a make file or the equivalent, and then it'll be much easier for you to play around with the code, because you can just change something, build it, run it in the emulator, and see what happens. Anyway, but don't be overwhelmed. They're just commands, and again, if you're not sure what a command does or what a certain parameter of the command does, you can just go off and look on the internet or look on the man pages of the command. But I'll explain these as I go through them. So what we're going to do first, we're just going to write some C code. Now, I'm not assuming that you've used C before, but you should be familiar with the programming language. And I'm just going to write some C code, compile it, look at what gets generated by the compiler, and then talk about that stuff. And I'll just layer up the examples to demonstrate more things until we've got enough information we need to carry on writing our kernel and booting it. Right. So if we look at here, I'm going to create a C file called functions.c, and in here I'm just going to create a simple function to start with. So So I'll call it function 1, and it's going to do a return 1, 2, 3, 4, A, B, C, D. Now, what have I done then? So I've just defined a function in C. It should look familiar to most people that know any programming language. It's got a return type, an integer, and it's got a name, and it returns a value, which is just a fixed value here. And the reason I've used this value, this distinctive value, is just so that when we look at the binary, we can recognise it in there, just to help us feel our way around the binary. So now I need to compile that. Now, just clear that. When I compile it, I'm going to use this instruction, which I'll explain. So I'm using GCC, which is a popular open source compiler. Supports all kinds of architectures and different configurations, and it can be used for building processes, just normal processes that you run in an operating system, but it can also be used for compiling operating systems. And I'm using some very simple modes to compile my code now. So what I'm doing here is basically I'm calling GCC, and the input file is functions.c, which is where I just declared that function, and the output file is functions.o. And when you see a .o file, that's an object file. So, and don't get confused with object orientation and things like that. An object file is just it's really just an intermediate stage where you've taken some C code or from another language and you've compiled it into assembly, but it's still not assembled ready for loading into the for actually executing. It's got a lot of stuff in there to help you translate addresses and stuff in there before it gets put into memory, because you'll know from when we looked at the early boot sector stuff that it's important to know where things are in memory. And when you call a function, the CPU doesn't know what a function is, it just calls an address of where there's some code. So this object code level, and I'll show you, I'll do an object dump of this file to show you how it's structured, but it's got extra information in there like symbols, which a symbol is just a name, like a function name that maps to an address, and it might have some relative addresses in there that just before it gets loaded into the operating system, say on Windows or Linux, then it will get mapped into an absolute address in memory. So that's what it's doing. These other options, so freestanding is just, I've got some references in the notes file. It's just a page I found that describes some of these things, but freestanding just means that we're compiling our code not to run in an operating system, but we want it to run on its own. It's going to be an operating system, it's going to be a kernel, so it's not expecting to link to any standard libraries that you would find on an operating system, because there are no libraries. We're working at a very low level, so we are the operating system, so we configure it. We configure the compiler to say that it's freestanding mode. Okay, and the other thing here, I've got M32, which just means it's going to compile 32-bit code. I'm actually running these examples on a 64-bit machine, and by default, if I compile it, it will compile to 64-bit code. But in the last lecture, we learned how to switch into 32-bit protected mode, and that's my target for my kernel. So I'm going to be compiling my kernel code in 32 bits. So this is my command. So I've compiled the code now, and I got no output, which is normal when it all works. And now what I'm going to do is just show the assembly that was generated in that code, and we're going to just cross-reference that really with the C code. So I'm doing an object dump now. Object dump just takes an object file that's been created by a compiler, and it just gives you some information about it. It lets you display what's inside it in a nice usable way. So I can look at the assembly instructions, I can look at labels and things. I won't talk too much about object files, but often they have different segments in them, different sections in them, describing information about the executable code, and there might be meta information like which compiler generated it, what architecture it's for, and stuff like that. So there's lots of stuff, lots of meta information goes in an object file about the compiled code. Now, I'm going to just run this now. So what we see here then is this is all that's in that object file in terms of code. And so we see the symbol there, function1, and that's just mapping to this address 0000. So basically function1 maps to 0. So this is the address within the object file of this function, function1. And if I go back to my code, yep, okay. So on here, where's my code going? If I bring my code, so this is my function. So this is my C function, and what I'm seeing here is the assembly code that the compiler generated for it. And you often see these common patterns, and let me just explain this because it's important. This is all the code for that function that returns that value. Well, first of all, we can see the value here that gets loaded into the EAX register, and a convention for the compiler is to use the EX register for returning from a function. So once a function's been called, the place that called it will check the EAX register to see if there was value returned, and here it's just storing this integer into that EAX register. Remember, the CPU's got no concept of functions; it's just addresses, and and the way it passes arguments to them is on the stack and through registers. Okay, so first of all, these two lines here, so push EBP, this is just saying take the current stack base pointer and push it onto the stack. It means that we're going to be changing the stack base pointer, and we want to be able to restore it later. Okay, when we've when we've modified some, we've created our own stack inside our function. It's called a stack frame, and it's used for local variables, which we'll see in a minute, and also for referencing arguments that are passed into the stack, into the function. So we see this, so it's push EBP, we store the EBP pointer, and then we store the, we update the base pointer of the stack to the current top of the stack. So what that means effectively, that we're just taking the original stack before the function was called, and we're remembering where the base pointer was for the stack, but then so we push that onto the stack, and then we update the base pointer to the top of the stack. So we've got an empty stack again now, and you'll see when we create local variables, we'll increase the top of the stack within our function to put stuff in there, and then once the function returns, we'll restore the original caller stack. Like I said in another lecture on calling functions, it's important that we don't have any strange side effects for the caller once they call the function. So when the function returns, everything, the registers and the stack, unless it's some special case, should all be back in the state they were before it was called. So that's what we do. We create our stack, and then we restore it again before we return. That'll be clearer when we look at a more involved example. And then what do we do at the end before we return? We just pop the original base pointer from the stack that we pushed on back into the base pointer register. So we've restored the base pointer again of the caller stack, and then we call return. And the return function, well, we've looked at that before, haven't we? That just restores the, it takes the instruction pointer that was stored on the stack by the call opcode, and then it starts execution of that instruction pointer again. So that's the code for this function. Okay. Now let's just update it a bit. If I create an integer like x, if I say int x equals 2, so in my high level language what I'm doing is I'm creating a local variable inside this function that I use for storing things inside the function. Outside of the function it's not going to be used, and we'll see when I compile this one. So if I recompile that code and then do an object dump, we'll see the updated code now. So again, the start looks similar, it establishes the stack, but then it does this thing here, this sub ESP 10. Now that 10 is in hexadecimal, and that means 16. So what it's doing is it's saying take the stack that we've created, our local stack frame. Remember I said we when a function starts, the compiler initializes a local stack frame, an empty stack frame, by incrementing the base pointer of the parent stack frame to the top of the stack, so it becomes empty like this. And then what it's doing here is it's taking the top of the stack and it's adding 16 bytes onto the top of the stack. And these 16 bytes, they're not all used in this case. Often more space is allocated than is needed, just to do with performance reasons on the CPU. So it's allocating 16 bytes, and then what it's doing here is it's moving my value 2 into this address here, which is the base pointer minus 4 bytes. 4 bytes because it's an integer and I'm on the 32-bit system, so 4 bytes is 32 bits. So it's basically storing that integer value into this stack that it's set up. And the CPU's got no idea about variable names and stuff like that, or even types of variables, in the sense that we think of when we're writing our code in a high-level language. It just stores them on the stack, and when the code references that variable later on, then it just references it as an offset of the stack, the current stack frame. So what it's doing here, it's saying EBP, so the base pointer of the stack. Now remember that actually in memory the stack usually grows downwards, so the base pointer is at high memory and the stack pointer is below it, and that's why when we add to the top of our stack, we actually decrement the stack pointer. The stack sort of grows downwards. Whichever way you think of it, you need to know how it's implemented in memory, but you can think of it going upwards or downwards. Doesn't really matter, but in terms of how it fits in memory, it grows downwards, and that's why we have this sub here. So what this is referencing then here is just saying move the value 2 into the address that is take the base pointer, so our current stack frame for our function, and get the space that's occupied by the first 4 bytes in there. We're going to store this integer. So that's how it does it. That's how it stores an integer. So that's how this code gets implemented. So this 2 just gets stored on the local stack frame. Now let's create another function and see what happens. In fact, I'll keep these. I'll preserve these functions, and then we can easily compare them when we're looking at the output. So now if we take this one and so we've got x equals 2, and now let's suppose that we do int y equals x. So we should be able to imagine what's going to happen. We'll try and imagine it before we look at the code. So we've got this x, and we know that that local variable is established on the stack, the local stack frame of the function. In terms of assembly, that's how the compiler realizes these local variables. And then we take another local variable, so we're assigning some more local space, and we're copying the value in x into y. So we should see how, for example, x is referenced in assembly when it does that copy. And we won't see any x's in the assembly because assembly doesn't care about variable names. Okay, let me just put that in the top. So now we've got this function 3. So what's it do? It looks the same as this one initially, so it's still setting up, it's allocating 16 bytes on the top of the stack for the function, so in the local stack frame. And what it does, it takes this 2 and it stores it in part of that stack, in the first 4 bytes of that stack. And then we see this thing here. So then what it does is it takes the contents of EBP minus 4, which this address is x. So we can think of this, the compiler is basically using this to represent the x variable. So whenever we see this in the code, it's representing that x. because x is just an offset from our base pointer, our stack base pointer. Sometimes you see the base pointer used as a reference, a relative reference for where things are in the local frame, and sometimes you use the top of the stack ESP. It doesn't matter which one you use, because the compiler can work out where your variable is based on one or the other of those stack pointers. Either reference it from the top, so it's plus something from the it's minus something from the top of the stack, or it's plus some index from the bottom of the stack. So what's it doing? So it's storing that into here, into that location where the x variable is, and then it's doing this thing here where it's taking the contents of that address on the stack, which is where it stored the 2. Remember, the brackets mean store it in the address held at this place, and then and it's moving them into EAX, which is a register, and then it's taking EAX and it's copying that one into this position on the stack, which is 4 bytes below the other variable. So we see here that it's referencing 2 variables on the local stack, x and y, and it's taking the value of x. Is that what I called it, x? Yeah. It's taking the value of x and it's storing EX just temporarily, and then it's moving it from EX into y. So you'll see that it doesn't move directly from, the CPU can't move directly from this memory offset to the other memory offset. It has to store it in a register in between. And remember, sometimes when you think of a higher level language and you look at assembly, you think, oh, it should be able to do this and this and this, but actually the assembly is sort of finely tuned around the hardware, the capabilities of the hardware, to do very simple things very quickly. And that's why often when you're doing something you have to move a value into a register and then move it into another location in memory. So you can't move it directly between the spaces on the stack. And besides, the stack is actually implemented in memory and the registers are implemented in sort of very fast local CPU memory. So they're very different how they're handled. So that's how that works. So we see then that go back here. So we see that 2 gets stored in x, and then the value inside x gets stored in y, and then we return that value. Now let's look at another example of a function. If I do let's try and add some numbers together. So I'm going to take 2 arguments, a and b, and I'm going to return a plus b. So let's see how this gets compiled. And this is a really good way of figuring out how the compiler works, and also learning about assembly. And also, if you change certain options on the compiler, like to optimize code, you'll see different instructions get used, and sometimes the assembly instructions get flipped around so that they seem to be in the wrong order. And so the code works in the same way. It's just that sometimes different instructions might be used and stuff. But it's good to just play around like this, because then you can figure out how it works. You can't always find the information that you want in documentation. Sometimes you just have to try it and see what happens. So let's see what this does. So it's called add. It takes an integer a, an integer b, and it adds them together and returns the result. So let's just, before we look at the code, let's guess what's going to happen. Well, how do these arguments get passed into the function? Because remember, a call is a low-level opcoding assembly for calling a function. And there's no way of passing parameters other than putting them on the stack or putting them in registers. So it's going to either put these in registers or on the stack. And then when it returns a value, well, we saw before that usually the compiler puts the return value in the EAX register, so we imagine that the result will get stored in there. And at some stage it will add these together, so there should be some add instruction. So let's just compile it and see. What I'm going to do, I forgot to compile it. So we compile it, and we render it. So this is my add function. So let's have a look what it does. So it sets up its stack, Now in this case we see that although it's set up its stack here, it's not actually used the stack, it's just done this thing here. Something the compiler usually does, it usually sets up the stack even if it's not used. I mean the local stack frame. So there's no, in this function, there are no local variables in this function, there are only arguments that get passed in, and then it just returns the result here. So there's no local variables, which is why we don't see anything on the stack in this case. So what it does then, it uses these two references here, which actually reference the arguments A and B. Now you'll see here that a telltale that these are arguments is that it's the base pointer of the stack frame plus an offset. And we'll see for local variables, like we saw before, that we see a minus. And it's just because I've got a picture of this somewhere. It's because the stack base pointer, it's because the caller puts the arguments onto their stack frame, and then when the function is called it sets up its own stack frame, it updates its base pointer. So anything that the caller put there is going to be outside of our local stack frame, it's going to be below our stack base pointer, but things in our own frame are going to be above our base pointer. But remember also that stack's upside down, so in terms of the actual offsets, it's, when we say above the base pointer, it means below it in memory. It does get confusing, but that's how it works. So so this is the code that it generated. Let me just find you a diagram of that I found on the web. I'm not sure who made this. It was just a simple, I thought it was a simple picture. Okay, so this is just showing what the stack looks like. So we see that on the stack we have the base pointer. We have this is the base pointer of the parent stack that we store when our function's called, so that we can recover the stack frame. And then we'll see that we've got the arguments above the stack frame. I mean, they're sort of outside of our stack frame, and we've got the local functions, local variables inside our stack frame. So that's, you can see that using the offsets here, plus and minus above and below the base pointer. So that's how the stack looks. Let's go back to our function. So this one, yeah. So there's our assembly. So it's referencing the arguments here. So it's saying take the argument, the integer value that's stored at this offset above the base pointer in memory, and take the other argument that's stored at that address. So C is 4 bytes higher than 8, which is right because these are integers and they're 4 bytes wide. And then you'll see here, so it loads those arguments into these registers EAX and EDX. It doesn't matter which registers it uses, the compiler just has to use whichever ones are available, because it's only got a finite number of registers, and if it needs to do too much stuff, then it's probably going to start pushing things on the stack and stuff. You've got to make the most use of your registers. And then it takes the values that were taken from those arguments, and it just calls add on them and adds them. And conveniently, EAX is also the return, the register that's used for returning values from a function. So because we add EDX into EAX, then you don't need to copy into EAX again. The result will already be in there. It will be there to be returned. So it returns a value added. So you can see that how the compiler is generating disassembly from the C code that we write. I'll just look at a few more examples, then we'll get on to booting our code. We've also got to process these a little bit more. We've got to link them. I'll explain that in a minute. So let's just try something else. So let's call that function. So I'm going to write some code now that does int result equals add to 3. So the caller is going to call this add function, and it's going to pass in a value 2, an integer 2, an integer 3, and it's going to store the result in there. So we'll see how the call looks from the caller's perspective. We'll see how it sets up those arguments on the stack for the function that's called to grab them. So let's just compile that. Okay, so now here's my caller. So again, it sets up its stack. It's setting up some space on the stack here for storing its local variables. Now in this case, actually, it's not storing. If we look at the code, it does have it's got an int that it stores in local space, but it seems to have taken up more space on its stack than the others did. It's taken 18, so it's 18 hexadecimal. So it's created that space on its stack. It's not only created that space for its local variables, but it's also created it for the arguments that it's going to pass in to the call function. So what we're seeing here then is that if we look on, so we've got these numbers 2 and 3 in here. We'll see how those are stored. So first of all, it stores the 3 into here. The arguments are actually put on the stack in reverse order. I'm not going to go into this now. If you want to, you can read more about C and how it works. Doesn't really matter, it doesn't change the explanation. We're just looking at how it works. So it stores this number 3 into this position on the stack. So it's some local variable. So effectively it's just using, although I didn't declare like int 3, int 2 within the function, the compiler still has to do the same anyway, because it means the same. If I declared them like that, then I could just pass the variable names into the function rather than the actual values. Anyway, so it creates the 2 and the 3 on the stack, and then it just calls this function. Now this, we see the call statement here, call 5b. All this means is that this is just working out the address of the add function. So if you work this out, caller plus 16, if you take this caller and then you let's have a look. So this should be 16 bytes. It's 45 minus 16 bytes will give you 38. So it'll give you the start of this address there. So this is just calling the add function. So we'll see the symbols used in here. Now when we come to compile it ready for our kernel, these will all get translated into absolute memory addresses based on where it will be loaded in memory. But now we just see using symbols like this. Anyway, it calls that function after we set up the variables on its local stack, and then it just takes we see it taking after the call is finished, we see it take the value of EAX and we see it store it onto its local stack frame, and that's just because it's storing the result of the addition into a local variable there. Okay, so just a few more bits that I've not explained yet is that when we set up a stack frame like this, where we do, for example, we store the caller's base pointer, and then we update the base pointer register to the top of the stack to create our empty stack, and then we add some space onto the top of the stack for our local variables. And once we've done that, we've got to restore the stack for the caller once we return from the function, and we do that just by calling leave here. So leave will it'll just bring the stack back to the original state that it was in when the caller called us. You'll see here that leave is used here, but it's not used in this function, and that's just because you'll see that the compiler is just using leave to negate this function here. It's only when we actually set up some local variables on the stack that we use leave. Otherwise there's no point calling it because we don't need to. So we should recognise that this code that the compiler is generating is very similar to the code that we wrote manually in some of our boot sectors, which is good because we see that C is just assembly really under the surface. Now let me look at some more examples. Probably I'll finish after this and then we'll get on with the other stuff. But if we have a look at what pointers are, if I do another one here, if I do int, call it add2, and I do int pointer A, int pointer B, and I do return dereference A plus dereference B. So people often, when they're starting to learn C, they get worried about pointers, but we'll see that pointers are just a natural part of the computer, really, because that's how, because we really, variables are just addresses in memory, and the fact that C lets us manipulate pointers just gives us direct control of the memory. We can access a particular memory address directly, and we'll see that's important later on when our kernel boots. We'll need to do that. So let's just look at how this is different to the other one. So what we've got here is a pointer to A and a pointer to B. So a pointer just stores the address of something that holds a value. So it's not actually passing the values themselves, it's passing the addresses of where those values are stored in memory. It's called pass by reference as well, so we're not copying values into the function. We just set up the values, call the function, and the function works on those values that we set up, just because we give it the addresses. We tell it where to find them. So, and then we return them. So the stars here just mean don't add the addresses of A and B, add the values stored at the addresses. So this is dereferencing it. Let's just look at that code. So this is our add2. So if we look at our add, so this is our add1 that just does without pointers, and this is our add2. So we see with the add1, if we look back at it, that it takes the values that it adds in EAX and EDX are it loads those values with the contents that's stored in the address of the arguments that are on the stack. Okay, this, if we look at this example here, it's using pointers now. So yeah, first of all, it takes the base pointer value, and it just moves that it's in EX here. It's not storing the value of the number, it's storing the argument that was passed to the function, which is a pointer. It's an address of the value. So here EX holds the address of one of those integers that were passed in, and in this case it holds the value of one of those things that were passed in. And so what that means now then is it has to dereference it now. So it's going to do the addition, not of the addresses that are stored in here. It's going to take the contents of that address, so using the brackets here, and it's going to store that in EDX. So EDX should now hold the value of one of those integers, and we'll see it does the same here for the other integer. It's exactly the same. So now we've got that EDX holds one of the values and EX holds one of the values, and then it adds them together just in the same way it did then. And so you see that there's some extra commands here, and that's just because it's got to dereference those integers. So that's how a pointer looks. Really, this is quite natural in assembly when you look at the use of addresses, because that's all you deal with. You don't have variables, you just have addresses. So you kind of remember where things are stored, either in reference to the stack or in reference to memory. And that's how pointers work in C. Have a play around with that. Really, it's one of those things again where you can, it doesn't always sink in at first, but if you just go through some examples like this and use similar commands to what I used there, and look at the assembly that's generated, and just play around with different C code, and you'll see how the C code gets implemented. Now the important part for us is that we're going to be creating our C code, and we want to know what the compiler generates. So at the moment, when I do this compile thing here. I'm actually clear my screen. I'm creating this object file. Now, I can't take this object file and load that directly into memory, because it's not just a binary file. It's not just got code in it. It's got loads of metadata for linking it with other things and for describing the architecture and stuff. And for my kernel, I don't want any of that stuff. I just want the raw code that was written, or any data that's in there, any constant data. So I need to process it a bit more. So what I need to do now is I've created my let's start to work on my kernel now. So if I, in a similar way, I'm going to go working, let's call it kernel1.c. So this is like my kernel file. I'm just going to create a function called main, and I'll call it entry. So this is where we enter the kernel. And in there, let me just do, just so I can see the actual code, let me do int I equals x 1 2 3 4 a b c d. Okay. Now what I want to do is compile my kernel code, just like I did those example functions. Kernel1.o. So I've created the object file now. I should be able to do an object. I can do an object dump. So this is my kernel code that I just wrote. And my goal of this whole thing is to take this code that I've compiled and with my assembly code, my boot sector code, load it in from the disk, and then start code executing inside here. And then once I've done that, once I've passed control into the C code, it's easy for me then to start creating my operating system in a high level language, using all the abstraction that C gives me rather than assembly. So this is what I want to do. So let's have a look. So this is our code. It's just a very simple function, but we'll see that if I it's always good to use your hex editor. If I get a hex editor on this object file that I just compiled, what I'll see is that although this is the only code in there, so this is all I'm interested in actually executing when I boot it, my operating system. Although it's only got that code in there, but if you look at all of this stuff, the file is full of metadata and stuff, and you see there's mentions of ELF, which is an executable file format. It's got metadata in there. It's got some symbols in there like entry for my function name. So it's got a lot of stuff in there. So this isn't just a raw binary opcodes that I can execute in the CPU. This is more something that that we would take and translate into a binary, which is what I'm going to show now. So what I need to do now, if I close that, is take my, let's do this. Okay, so what I'm doing now is I'm taking this object file I compiled. So I compiled this thing, which is what had my code in, but it also had a lot of metadata in. And I need to turn this into a format that can be executed on the low-level machine. So just raw code and data. So what I do is I use the linker, so LD, and all the linker does is it takes these intermediate compiled object files and it puts them all together into a binary file. And it can do that in different ways for different environments. If I'm compiling stuff for to run on my Linux machine, like like for my desktop or something like that, then I want to leave all of that metadata in there, so that my operating system knows how to load it and stuff. There's information that tells the operating system what to do with the image once it loads it in, where to place things, things like memory protection, if a segment of the the memory should be non-executable and stuff like that. But I don't care about that stuff at this low level. I just want to get the raw code. So I take my linker command and I say take this object file and output a binary file and I want that in format binary. This just means I want just the raw binary data that I can just execute on the machine. So basically just strip out all of the rubbish. Now these are the things here. So firstly I've got to tell it that I want it to be a 32-bit 86 code, so I put this in here. You can look more about these options on, if you look at the man page for LD, the linker, or on the web you can find out more about them, but you can change the target of the linker, just like we changed the target in the compiler. And anyway, the linker, the target architecture of the linker should be the same as that we compiled. And remember we put 32-bit in the compiler command line. And this bit here, text 7E00, what this means is that, do you remember in our boot sector code that we had at the top of the boot sector we had a statement that said org and then an address. It was I think it was 7C00. We had to put that origin in there, so the assembler knew that once the boot sector was loaded into code it knew where it would be, so it could calculate the absolute addresses of labels and things that were called in the code. And it's the same for our kernel now, because we're going to be loading it somewhere in memory, somewhere specifically in memory. So we need to tell the code and the linker how to translate those symbols and things into absolute memory addresses, so that when I do a jump to a label in my, or call a function in my C code, that function name maps to an absolute memory address in memory based on where it was loaded. And that's what this does here. You can play around with setting it to the wrong value and seeing that your code will fail to work. It's not always, it doesn't always fail. It's sometimes the instructions that the compiler generates use relative memory. So it might say, like to call a particular function, it might not say call it at this particular address. It might say take the current address of something, some local reference, and just jump to a few bytes above or below that. So it can be a relative memory as well, which isn't affected by absolute addressing. But if you've got global variables or things like that, or the compiler generates any global references, then you need the code needs to know where it'll be loaded into memory, just like our boot sector did. So that's what this does here. When you see the word text, it's a bit misleading, but text really means code. So when you see references to text sections in code, it means, in a binary file, it means the text, it means the code, and you've usually got text and data in there. So it's saying, this is saying my code is going to be loaded at that address. Okay, let me link it now and create that binary. So this is okay, you'll get a warning there, that's fine. So now what I should have, if I look at this file here, this binary file, I should see that I can use well, yeah, I can use ghex like I've got here. So let me just open the hex editor. So I'll see now that this code, there's not as many bytes in there as there was in the object file, because all of that stuff has been stripped out now. And this is just my code. And if I look at some of these bytes here, for example, 1, 2, 3, 4, A, B, C, D. Remember the architecture is little endian, which means that the least significant bytes come first in terms of how it's stored in memory. That's why 1, 2, 3, 4, A, B, C, D is in reverse order. But we see this is part of my code. So if we look at my kernel code, where are we? This is this number stored in there, I'm seeing in the raw binary file. Now it's got some other stuff in there, and I'm not sure exactly what else is in there. Basically it's got the code at the start, which is what we wanted, and it's got like these instructions here. If we look at, see these bytes here, so 55, 89, E5, 83, these are these bytes here. So this is showing that our opcodes for these instructions are at the start of the binary, which wasn't the case with the object file. There was a load of other header stuff up there to explain what the object file was. So now we've got the raw binary code in this file. There's some other trailing stuff as well that was added in there by the linker. it doesn't really matter because we just won't ever get to that code. We just want, once we take over execution at the start of our code here, we can direct the flow of code. Anyway, this is a minimal binary file that can be loaded into memory now, which is what we wanted. So that's good. So I compiled it, and then I used a linker to take the object file and turn that into a raw binary data file that I can load into memory. So what we need to do next, we're not quite finished yet. We've got to revisit our boot sector now. So what we've got so far is we've got our kernel image. Let's just improve this slightly, so that if we do land in this code from our boot sector, we'll go into a loop. So I'm just going to put a while loop in here, which is just the equivalent of a jump to the current address. And it just means that if we do get into this code, the computer will just go into a spin, so it won't crash out, it won't carry on executing code after this, it will just hang, just like we did in our boot sectors. So let's close this down for a minute and just recompile it. So I compile that kernel, and then I link it into this kernel 1.bin, and our goal now is to load this, use our boot sector to load this, to bootstrap this kernel, this C code, and then transfer execution to it, and then we've suddenly got access to C. We can start writing our kernel in C, which is nice. So let's have a look. So what we've got to do, we've got to go back to our boot sector again. Now, if I go here, this is my boot sector, and this is where I left off in the last lecture. So all this boot sector does at the moment is it uses the routines that we established in the previous lectures and the last lecture to switch into 32-bit protected mode, but then it just hangs once it gets there. So we print out a message say we're in real mode, we switch to protected mode, and then it just hangs. And what we're going to do now is look at how we can load the kernel that we just created. So, okay, let's just check this code works. So if I get my instruction here to create my boot sector, what I also want to do is just check that it's working. So I'll assemble my boot sector and then I'll run it. Boot sector using my QEMU. There we go. So we know it's working. So it boots up and it switches into 32-bit protected mode, which is where we got to in the last lecture. Good. Now what we're going to do, well, so we're going to load our kernel. First of all, let's just print some more messages out. So let's just add a message down here, just to say what we're doing. So we'll say message loading kernel. Okay. Loading kernel from disk. So that's what we're doing. Remember in an earlier lecture we looked at how to load stuff from a disk. Now, the first thing that we can do is, let me print this message out. So, we get very little feedback at this level, so we need to just, if we can print out stuff at certain stages, then it gives them an idea what's happening. So, yeah, that's alright, so it says loading kernel from disk. Now, if you remember in the last lecture, when we switch into 32-bit protected mode, the problem is that we have no access to BIOS. So if we want to load something from the disk, we'll have to write a disk driver, manipulate the hardware directly, which we can do. Although a trick is to load the data before we switch into protected mode to where we want it, so that when we're in protected mode it's already there and we can jump into it. So if we do that, we can use our functions from before using BIOS to load the data. So that's what I'm going to do now. So once you've loaded, so you can do things like little tricks like this so that it's easier to get into your C code, into your 32-bit protected mode. Then once in C, you can start to, it becomes more realistic to write, a piece of complex driver to access the disk or something like that. Whereas if we try and do too much in assembly in this early boot process, then it's more complicated for us. And that's why often you have stages of booting, which is the definition of bootstrapping. You start with something simple, and then that builds, it sort of introduces something else, and then that introduces something else, and you just build it up. So we're going to load our kernel. Now what we can do is we've got to think about what's happening here, because when BIOS loaded our code, it loaded just one sector into memory, our boot sector. That's all it loads from the disk, the first sector. So our kernel, we're going to prepare the disk so that our kernel occupies the next few sectors of the disk, and we're going to, and our boot sector is going to load the next few sectors from the disk, and a convenient place to put them for now is just right after our boot sector in memory, so that we can easily jump into that code using labels. I'll show you, I'll explain that, but we know that our boot sector code loaded at this address in memory, 7C00. So the next sector, the address of the next sector is 7E00. So that's 7C00 at 512 bytes, which gives you 7E00. And that's where we're going to load the kernel to, and then we're going to jump into it. And that will put the kernel down here. I can create a label already. I can say kernel entry. So kernel the kernel code will be loaded there immediately after our boot sector. So this is the magic number right at the end of our boot sector, and the next bytes will be in the next sector, which BIOS didn't load because it only loads the first one, but we're going to manually load those from the disk to this address immediately after our boot sector, and then we should be able to jump to that address and jump straight into our C kernel code. So it's just a nice way of doing it. So what we can say then, this address actually, kernel entry, will be I'll say where we load it. So loading kernel from disk to address 0x7E00. That's where it will get to. That will be that's what this label will refer to. Okay, so that's good. So we've got to load our kernel now. So we can use that function that we created before. And I'll just show you the code of that. So what I want to do is I'm going to call this function, call read from disk, we called it. So you can see how just in the last lectures we built up these functions, like for printing strings, for switching to protected mode, and for reading, using BIOS to read sectors from the disk, and we can start to use them all now. So I'm going to call this function, but before I call this I need to pass some arguments to it. If we look at this function here, I've just slightly modified it for this example. You can look in the last lecture at how this works, but basically it's setting up some registers, and then it's calling a BIOS interrupt that causes the disk to be read. So it causes BIOS to read some sectors from the disk and store them in memory. And I've commented out some of the parameters to BIOS so that we can pass them into the function manually. So one of them is the number of sectors to read. So here, when we call this function, we need to set up the AL register to the number of registers we want to, number of sectors we want to read from the disk. And also I've commented out BX here, which points to the address to load it to. So we've got to pass that in. So BX and AL we need to pass in. Yeah, so if I go, how many sectors do we want to read to AL? I'm going to put 9 because it's, when I was playing with this, 9 is the most we can read without switching to a different cylinder on the disk. I won't go into all of that now, but we're going to load the first, well, the next 9 sectors after the boot sector. And then we want to say where they're stored. Where do we want BIOS to load them to? We're going to load them to kernel entry. Yep. So we store kernel entry now. This kernel entry, because I've organised my code like this, this label here will be immediately after my boot sector. So this will also reference the address that we're loading kernel to, 0x7E00. Okay. I'm just using the label for convenience. I could just put that address into here where it says kernel entry. So what this should do then is it should it should load my kernel now. Now the first thing I'll see when I run this just to go over that again. Sorry to repeat stuff, but sometimes I need to. It doesn't always sink in. So what I'm doing is I've booted my boot sector's booted. BIOS loaded my boot sector into memory. I printed some strings to say what I'm doing. I started in real mode. Before I switch to protected mode here, I'm going to make use of BIOS before BIOS becomes completely useless. I'm going to use it to read 9 sectors following the boot sector that was stored on my disk from the disk into memory to this address. And then my goal is, once I've switched into protected mode, I'm going to jump into that address of my kernel that's loaded, which is 32-bit code. So when I'm in protected mode, 32-bit mode, I'll be running my 32-bit code. So I need to load it here. Let's have a look what happens. Okay. Now you'll see here, if you look here, there was an error reading the disk. It printed that message in my disk routine to check when there was an error. And this is because I've not actually prepared my image with my kernel. So far what I've done is I've compiled my boot sector and I'm running my boot sector in QEMU. But what I actually need to give to QEMU is an image of the disk with the kernel sectors also in there. So I need to build that image, and only then will it be able to read those extra segments into memory. Otherwise I just get that disk error because there are no extra segments. I've only got my disk that I passed to QEMU, and here it's just comprises of my boot sector code. So I've got to do a bit of manipulation of the files now. So what we've got to do, we've got to build our disk image. So first of all we need to assemble our boot sector. I've done that. And then what we've got to do is take our boot sector and concatenate that with our kernel binary that we generated up here using these things. And we just put that into an OS image binary, which is just the boot sector, and then concatenate it with our kernel code. And this is this that we're going to load into QEMU. But if you remember from the last lecture, I mentioned that if in QEMU there aren't enough sectors for it to try to read, or the last sector isn't a whole sector on the disk, then QEMU you'll get an error when you try to read that sector. So I also just pad out that image with zeros. I just pad it out for 20 sectors so that it's just to make sure it's long enough for it to read the first few sectors that have my kernel in them. And then I run that image, and I should land in my C code. Let's see if I don't make a mistake, which is always easy to do. Right, so what have I got to do? So I've created my my boot sector, and now I need to concat my kernel and my boot sector to create an image. So I'm just using cat there. So join these two files to create my image. Yep. And now if I just do an ls working os image to look at it, I'll see that it's only got this many bytes in. It's actually not even big enough. It's not got if I try and load 9 sectors from this disk, it's going to fail because it's not long enough. It's just barely over one sector long, 580 bytes. So I'm going to use truncate, which confusingly also can be used for padding. If you tell it to, if you give it a big size, it will pad out the file with zeros at the end. So I'm going to take that image and I'm going to make it longer. And if I just do an ls now, I'll see it's 10k long now. So it's got about 20 sectors worth of data in there with just zeros at the end. So it should be big enough for my QEMU to read that. And now I should be able to take my QEMU and boot it. See what happens. Okay, so it loaded. It didn't. There was no error loading from the disk, which is good, but it's still not really done anything. And there's a few reasons why, because we've not told it to do anything yet. But I'm assuming that it's loading the data, which is good. That's what we wanted. But now we need to jump to the kernel code. So let me just close this down. So if I edit my boot sector, edit my boot sector. So what I've got so far, I've loaded my kernel code into here immediately after my boot sector code, and now I just need to jump to it. At the moment I've just got this, I switch into, this is where I land in protected mode after I switch here, and I just hang. So what I want to do now is just do this, call, in fact I won't do call, I'll just do jump. I can just jump into my code. So I'll jump into kernel entry. And then I should land in my kernel code then. Which once loaded I should start executing in that first function, the kernel entry function. Let's just see if that works. Now, I said make was a good idea, so when you're doing this you should probably make yourself a make file, but for now let's just move it out of the way. Move it back, get down there. Now, I've just chained together all of those commands just for my convenience to save typing them. So all this is doing now is it's first it removes any image that's there already, just to make sure I start from a clean image. I compile my kernel into an object file and then link it into the raw binary file, kernel file, so I strip out all that metadata. I tell it where it's going to be loaded in memory, which is immediately after my boot sector, just so that it can work out the absolute addresses. And then I assemble my boot sector using NASM into a binary. Then I concatenate my boot sector and my kernel to give me my image, and then lastly I just pad out my image so that QEMU won't bail when a sector's not long enough. And then I run my QEMU, my machine simulator emulator, with this OS image, so the combined boot sector and kernel, which represents the disk, the virtual disk that the emulator sees. So it's going to should be able to read the sectors from this now. So let's just see what happens. Okay, so it says it's switched into protected mode and it's not doing anything. Still, we've not told it to do anything. What I'm hoping now is that it's landed in that loop in our C code. So if we want to prove that, we need to try and display something from our C code, and then we'll know we've landed in there. It's very hard, this kind of development, because you don't get, if you're working in an IDE and you've got a debugger and stuff like that, you can see what's going on, but when you're doing this low level development, it's very difficult to see what's going on. So you have to, you know, sometimes having a loop that just spins is more feedback than the computer's crashing out. So it didn't crash out, it hung, it seemed to hang in a loop, and the loop that it should have hung in should be my C code loop, but let's just have a look. Let's try and prove that. If I go to my kernel code here, and what I'm going to do now is, if you remember, let's just do this. If you remember before, in the last lecture, I said that we can't use BIOS to print characters to screen now, but we can print them directly to memory. And what I can do is, if I define a character pointer and call it p video memory, and I say that equals, I've got to cast it, I've got to tell it that it's pointed to a character. What was the address? I think it was B. Let me just check in my code. So the video buffer is at a particular address in memory, and if I use that, I can write characters directly to the screen. So if I look at what's this? So this is video memory address B80, so B8000 it is. So if I go back, B8000. So this is the address in memory. So I want to write a character to that. I'm going to write something. I'm going to say at that address in memory, I want to store a exclamation mark. Now, what should happen is I should see that exclamation mark, and then it should hang, and then I know that this C code is executed, and then I know that I've bootstrapped my C code from my boot sector, and then I can start writing my kernel in C. I can build it up. Let's just have a look. So I've got to compile it all again, build it all again. Ah, there she is. See that little tiny exclamation mark? That's my C kernel running. So now I can start to write in a high level language. Which is, that was our main goal really initially, to try and bootstrap some code, and we've got that now. So what I'm going to do is just, well, let's just make use of this. I can, a nice trick that I can do is, because I jump into the very first code in this binary for my kernel file, which is this function here, it's the first function, I'll just use this as a trampoline to jump into a main function. So I'm going to create a main function down here called, let's call it kmain, kernel main. And so in here I'll just call main. So it means I can put my kernel main function wherever. And this trampoline function, the first function, will always ensure that we jump into this code here. Now this is going to fail, but I'm just demonstrating something in C. Yeah, it's saying that in function entry there's an undefined reference to main. In your C code, you've always got to, if you start, because the compiler wants to generate code straight away from the C code, it wants to know what the things are, so I need to tell it what main is, because main's defined later in the file. So I just have to give it just have to declare it like this. So I say void, in fact that should have been kmain anyway, but void kmain. So I just declare it there. So this entry function will be the first function that runs, and it should run my kernel code there. Yeah, that's running. Now I'm going to build it up. You'll see it's much easier to write in C than it's assembly, so now I'm going to write a print function. We can do that just like, let's just have a look here. So what I can do, find a print function, takes a character, takes a string which is pointed to char, message, let's use a constant there, so if we call it video main Alex. So that's the video address, and then what I want to do is in here I'm going to create a pointer to our video buffer which points to that address, and then I'm going to create a loop now. So if I have an int I, I'm going to loop through all the characters in message until I get to a 0 character, the null character at the end of the string, and then I'm going to stop looping. So I can just, so what I need is a pointer to the next character, p next char equals message initially, and then I can use a while, but I can do while p next char. That's just going to say while the value of the character is not 0, because if I do while 0, this while it will stop. So while that's not 0, it's going to go around here. It's going to do, it's going to take the contents of video memory, this, and it's going to store the next character in it. And then what we've got to do is increment the next character, the pointer to the next character, the address. So we can do plus plus. And then what we need to do is increment the video buffer. But if you remember in the last lecture I said that each character is represented by 2 bytes in the video buffer, because 1 byte is the character and another byte is the like the properties of the character, the colour and stuff. So we increment the video buffer by 2 each time to get to the next character space in the video memory. So if I do video buffer plus equals 2, that should do it. So I'm just going to run that. I probably made a mistake, I usually do, but let's see what happens. So put a message in there, let's see if this works. Have I not made any obvious mistakes? Looks alright. Looks alright. Hey, there we go. We are executing in our kernel code. Good. So, what can we do? Oh, let me just close that. Well, we can build a barcode now. It's much easier to write in C than it is in assembly, even though C can sometimes seem a bit hard. After all that stuff we've been doing in assembly, like trying to make functions in assembly, it's so nice just to be able to do them in C. And once we've created these functions like print, we can just stick them in another file that we just build them together, link them together into our kernel, and then run them. So that's it. I'm going to just go over that again just to explain it all. All this code will be there in my notes for you to look at and play with. There's a few things you could do if you wanted to. You could now, one main thing that you would want to do is to probably set up something like the interrupt table, the protected run interrupt table. You could do that right in some C code, and then also create functions for reading and writing on I/O ports to devices for interacting with devices. And then on top of that, you would build up simple device drivers, maybe for the keyboard, or you might start like with the timer, the CPU timer, so that you print a message every time the timer interrupt fires or something like that, or you count something. But we've got C code now, which is, we've basically gone from nothing. We've had no support. We've just had the computer really. We've been writing assembly for, and we've bootstrapped our C code into the computer. So it's good. I'm just going to go through these again now. So what did we do? So we looked at C compilation. We took some simple functions in C and we compiled them and saw what assembly they created. And the reason I showed you that was because we need to understand how the binaries are created before we try to execute them from our boot sector. And we wanted to make sure that our kernel was, when we came to write the kernel, that it was just binary. It was a binary executable. It didn't have any metadata in there like an object file, so we had to strip it out using the linker like this. So we compiled our kernel, we linked it, we turned it into binary, and once we had our kernel and we had our boot sector, so then we wrote our boot sector just to use that function that we had before. If I go back to my boot sector, so our boot sector, what it does, it starts in real mode, it prints a message to say it's loading the kernel, and then it calls this function that we created in an earlier lecture to read from disk, and it reads 9 sectors from the disk, which we prepare our kernel image to concatenate the boot sector and then our kernel sectors from the compiled kernel binary. So we compile that into, we combine that into a disk image, which we then pass to QEMU, and then in our boot sector it just loads those extra sectors from the disk here, and it loads them to this address 7E00, which is the sector immediately after where our boot sector is loaded into memory. So it means that we can use this label here to reference it for our boot sector, because this label's right at the end of our first sector, which is right at the start of the second sector, where our boot sector code will be in memory. And we once we've switched into protected mode, and remember we did the disk read before we switched into protected mode, because in real mode we don't have, in the old 16-bit real mode, we don't have we've got access to BIOS to load stuff from the disk. BIOS is already loaded. It's got some basic drivers for the disks and stuff that it can help us with to load the data. So we load the data first to a particular memory address, and then we switch. I should be able to replace this here. If I say move this, I should be able to put kernel entry. Use my label instead to make it clearer. So we switch to protected mode, and once we make the switch over, we looked at that in the last lecture, I land here in 32-bit protected mode, and I just print a message to say I'm in protected mode, and then I jump to kernel entry. So this label will refer to this address in memory, which will be calculated by NASIM as the origin of where the NASIM code loads, the boot sector code loads, plus 512 bytes. Because our boot sector is exactly 512 bytes long, so this is where the kernel will be loaded into memory. So we just jump to it, and in our kernel code, it looks like this. So the very first piece of code that will execute, when this gets compiled and turned into a binary, the codes, the call function here, like call main, will be right at the top of the binary. It will be the first few opcodes in there, and so we just use this function to jump down to this main function. It just means we can move this main function around and we always land in it. So this is like a trampoline, I suppose, bounces us into here, and then we just hang after we've printed a message. And we can just define functions then to do things like print messages and stuff like that. So we've executed code in C that we booted, low-level code, so we had no operating system, we had no libraries. We just created our boot sector and then created our C code and executed it. And it's probably quite an interesting way to learn more about C, is looking at it from this perspective, because you do see it as a higher level language rather than a low level language. And you can really see how things like pointers work, like for example how I'm using pointers here to directly access a particular memory region, the video buffer, to print a string to video. You'll notice that if I put like /n in there, it's not going to give me a new line, because it's not got, that stuff that you have to write at this level. You just write into a particular coordinate on the screen. You'd have to manage all of your screen scrolling and stuff like that yourself. But there you go. So thank you very much. I hope you find the stuff useful, and maybe I'll look at some more stuff later on. There's lots of stuff you can do next. You could look at device drivers and stuff like that. Have a good read at the Intel Developer Manual. Look at the OSDEV wiki page. It's very good, and just play around really. So thank you very much.